Yep, and now it's in presentation mode. Perfect.
Great. Well, thank you for the invitation. The title of this is Energetic Material Formulations, as you can see. The subtitle is The Quest to Bridge the Gap Between Atomistic and Macro Scales. I'll give you a brief resume of that, if you like, but obviously we can't concentrate on all of that today. The co-authors here, I'm sort of the experimentalist here. Rick Anderson and David Bray are the main computational guys, and we've been working together for many years on this, and certainly couldn't do it without them. They're in the Hartree Centre, and if you like, I'm a bridge between the Hartree Centre and the world of energetics. And there, I've been working with the Falcon project for a number of years, and now I work ever so closely with them. And I'll say a little bit more about them later. The picture there is from our centre. This is a static firing of a rocket motor using the materials that I'll talk about today. This is based at Westcott, very close by to where we are now, and the idea is to solve problems here and improve the systems. Anyway, I know a few of you know about the rocket motors. I guess most of you don't. So what I thought I'd do is give you a quick overview here. And this here, the presentation here, just summarizes the three types of rockets. One is liquid. This uses a pressurized liquid fuel and a pressurized liquid oxidizer, and it pumps those into the nozzle and ignites them. And this is what you saw with those things like the launch of the space shuttle. The big orange vessel contains the liquids, and then the motor is here. But it also has solid rocket boosters, and you all remember those. These are jettisoned, and these are a composite of solid fuel and solid oxidizer in a solid mixture. And then there's the hybrid rocket, which uses pressurized liquid as an oxidizer into a solid fuel. Now, each one has advantages and disadvantages. The solid one that I'm going to talk about today is, if you like, the more robust, the simplest, and it has one big disadvantage, and that big disadvantage is once it's started, you don't stop it. So this is a cutout here of the solid rocket motor. It has a gap down the middle. The propellants on either side, if you like, in the cylinder. It has an igniter at the end and a throat to adjust the pressure. And then it's ignited and then it's off. I'll give you an example of the components here. It has an oxidizer, energetic crystals such as ammonium perchlorate. It has a fuel. An example there is aluminium metal. Now, mixing these things is not easy, and they have processing agents. One of them is a plasticiser, which I'll talk today about. It's all held together by a continuous phase, which is a polymeric binder. There are a number of these, but what I'm going to talk about today is hydroxy-terminated polybutadiene. So that gives you what's in there. This gives you an idea of the amount in weight of a simple solid rocket motor. You see, most of it is the oxidizer, and the more you can put in there, the better it is. The binder here, I put about 15% as the polybutadiene. We'd like to go lower than that. Then you have a fuel, the processing aids. The polybutadiene is cured, it's cross-linked, and you have a cross-linking agent, in there, which actually it is a rubber, so that fixes the rubber in the rocket structure. And then you have things like burning rate modifiers in there. So I entered this field not so long ago, and there were existing problems and a need to improve things. So as I've done quite often, we tried this, not tried, this is fundamental. You know, you have a theory, you do the experiment, and the idea is that each time we do the experiment, we try and do the simulation. Each time we get the results of the simulation, we justify that with experiment. You know, that's the way we've done this over the last few years. And the idea was to look into simulations at all length scales. And if we go on to the next slide, this gives you an idea of what we've been doing in terms of the length scales and the probe methods you can see. We have gone from the complete atomistic level. We've gone up, if you like, atomistically in scale, but we've also used coarse graining. We've done a lot of dissipated particle dynamics on this, and we're getting some really good results. We're also fortunate to have the ability with the Hartree Center to go into this exascale computing, so we can actually form really large molecules atomistically as well. So the idea being is that we want to see how the molecules react together, physically that is, and also chemically. But then we want to see how these are mixed, and then they behave differently, if you like, once they're cured on that. A lot of fluid dynamics, computational fluid dynamics has been done. We take a slightly different approach because what we wanted to do was to look at different mixing methods. So we've used lattice-Boltzmann methods to look at the particle movement. And then later on, although we've only done a small amount of this, we've used smooth particle hydrodynamics to look at the behavior in the later stages of mixing. So why would we want to do this? So you see one picture there of conventional mixing, and basically this involves blades rotating. And one of the things that I don't want to be close to is mixing energetic materials with rotating blades. Anyway, this is the conventional way of doing it. Recently, we've been using resonant acoustic mixing, and that's the picture on the bottom. This is really useful for highly filled composites of high viscosity media, and hence we've been looking at the different stages of this mixing, the wetting of the particles, then the percolation of the materials, etc. So the picture on the right, I actually took that in 2009 when STS-125 Atlantis took off. I was lucky enough to be there, and that was before I worked on this stuff, and never did I imagine that I'd actually be working on some of these materials. However, in 20 minutes, I can't cover all this. What I'm going to start is at the atomistic level to talk about how these materials interact and what are the differences between them. So what do they look like? So we've done a lot of X-ray tomography of inerts, but also live propellants. The two pictures there, one is a sample, a rectangle cutout of a live propellant. And the one on the right is from a much larger sample, but a circular cross-section cut out mathematically of this. And the particles are supposed to be spheres, and as you can see, they're not. But there are many, many things that we needed to look at here in terms of trying to make improvements. One was adhesion. the binder to the particles in there, the mechanical properties, of course, because these things have to suffer large amounts of vibration. And then there's the problems. You put in a processing aid, and then sometimes the processing aid in operation creates problems. And this is what's happening with the plasticizer. The safety and efficiency on this, obviously safety is a major concern. Then there's the curing and cross-linking. You know, what happens when you cross-link these materials? Can you make it better? What happens when the polymer shrinks? And also the ability to increase the energetic content is, especially nowadays, quite a big thing. So I'll give you an example here. I'll take the example of the plasticizer that's put into processing. Typically, dioctyl adipate is used. You can use other ones. You can process it. It's very difficult to process without this. However, it has problems. It likes associating with the cross-linking agent more than anything else. It's not completely compatible with the polymer binder. It tends to migrate out of the binder. And if you like, you can see this in other areas. If ever you've looked at a label, you know, stuck on with the pressure-sensitive adhesive, after a few years, you can see the oil that's put in a pressure-sensitive adhesive migrating out and even through the paper. Or even if you have something like a kitchen implement or something like that, that's been over-molded with the rubber. And a few years later, it becomes sticky. And this is because they formulate the rubber with a processing oil. And this slowly comes out over time. And I'm pleased to say, by looking at this scientifically, we've actually invented a new resin here that we can put into these things, which doesn't have these drawbacks. So if we keep on with this problem here, this is an X-ray tomograph, and you can see the ammonium perchlorate particles in the propellant, but also the binder here. And the situation is we can see differences in density of the binders. And with other methods, we've seen what this is. And this is due to the plasticizer migrating over time and forming its own little pockets in there. This is a model, the top one of the plasticizer, the dioctyl adipate. The new resins, we adjust the polarity. And in this case, we are adding an aromatic link in a stiff backbone. Actually, the backbone is dicyclopentadiene based. And to give you an idea of the sizes here, I hope you can see this. So the top is, if you like, the pre-polymer. This is the hydroxy terminated polybutadiene, molecular weight of about 3,000, hydroxyl functionality of about 2.5 per molecule. And if we expand that window, you can see the relative sizes. There's two plasticizers there, the new resin, and also the cross-linking agent, to give you an idea of the sizes. So with the molecular dynamics, we looked at that in detail. We looked at the mean square displacement measurements. This is quite a good summary, because this is at the end of about, I think, 100 nanoseconds. And the one on the left is the plasticizer. It was completely random in terms of the distribution. The gray is the polymer, the red is the plasticizer, and you can actually visually see, as well as numerically see, how this migration takes place. Whereas the new resin remains completely dispersed. We even went one step further, and we looked at a simulation experiment splitting them up. And after a computationally infinite amount of time, these remain the same, which means they really don't want to mix. Whereas we don't get this problem with the new materials. So I said, we want to look at how they interact with themselves and each other's. one interesting thing that we found here is the hydroxyls, not unsurprisingly, want to associate. And here you can see a few polybutadiene molecules, and the hydroxyls want to associate at the end. And if there's any water present, this exacerbates it, of course. So these are the curves, and as you can see, this gives you the number of molecules, i.e. the hydroxyls, in a cluster versus time. And they want to, if you like, slowly start increasing to about 4 hydroxyls. This is a bit busy, this, but I'll try and take you through it slowly. The top 4 images here are with the plasticizer and the polymer, and the bottom is with the newer resins. So these are atomistic, and this is using radial distributions. And basically, the closer you get to 1 here, means the better it is. The more it deviates, the more it wants to aggregate and phase separate. And the colors determine the time. So as you see with the plasticizer, the blue is the longest here, and it wants to aggregate together, whereas the resin beautifully goes to 1 here. We put in the hydroxyls association here as well with the polymer, and as you can see, you get many alone, of course, but then you get this this peak of association here as well. So how would I summarize this? It's important to look at the hydrogen bonding of these terminal hydroxyls. The plasticizer shows increasing self-aggregation with time. We can actually improve the plasticizer, but the best plasticizer doesn't exist commercially yet. And in fact, I wouldn't go that way, because the new resins actually improve the physical properties as well. And the effects of these different formulations on the diffusion of the components is important, because the plasticizer likes to link with the cross-linking agent as well, and therefore you lengthen the time for curing the propellant. And to give you an idea of the improvements, these are graphs. This is percent improvement, is when you make up a traditional blend with a plasticizer and you make it up with the new resin. And this is a stress strain, and so the maximum stress is considerably increased with the new formulation and also the strain. So if you like, this is akin to the best ways of formulating an adhesive for various applications as well, which is an area that I've spent many, many years in. So as a quick run through of this, we've, as I said, we've been lucky enough to transfer this to much larger scales, because one of the key things I wanted to do was to look at, see if we could look at cavitation. Most failures occur through cavitation. Where do they occur, etc. So we did these stress strain measurements on the computer. And here you see on the right the effect of stretching these molecules. This is atomistically. We're aiming to do this with coarse grain as well. And to look at the first nanoscale failures here. And as you can see, we've got not bad results for a very, very first try here. So we're going to extend these and hopefully start round about now. And because of the commercial aspects of this, we haven't published much of this. This has been presented scientifically, if you like. But in terms of the coarse graining, we have published 2 general publications. One of them was which is in the abstract. So I just wanted to show you this. I actually don't have a good video of the stretching and cavitation. So this is a handheld one, but it really shows the difference. So a conventional binder, if you like, is on the left. And if I stretch that, literally I stretch it, this is my hand doing the stretching, something interesting happens. So you get the cavitation taking place throughout. If we look at the modified binder, which is fascinating, we do the same thing. There was a bubble in there, but we don't see the cavitation, or the cavitation is too small. So that's a brief demonstration of linking the simulations, the molecules, etc., to make the improvements. And finally, I'd like to thank everybody here. There's Daniel Jubb and the Falcon team. These guys are tremendous. They are the best company I've ever experienced to work with and for. Michael Seaton from the Hartree Centre, he did the lattice-Boltzmann methods, which we haven't discussed, and the exascale stuff by Seddon and Guadalupe as well. Very many thanks to the various departments of MOD. We're doing this for to help the country, help the UK here as well, and we work very closely, and it's been a pleasure working with those. The cross-linking in the rheology, which we haven't covered, at the University of Oxford. Looking at the diffusion experiments, like mean square displacements, we tied that in with the University of Greenwich. And finally, the tomography work was done at the Diamond Light Source and the University of Manchester. So I've raced through that. I apologize for the speed, but it's difficult covering such a wide area on this.
Thank you very much. That was very interesting. We have some questions in the chat already, and I have some for myself as well. So Robert asked, what force fields did you use? Were they published ones, or were they developed specifically for this application?
I'm sorry, could you repeat it?
Sorry. What force fields did you use, and were they developed ones, or were they developed specifically for this application?
No, they weren't developed for this application. We used a number of force fields on this. Oh, I'm trying to think which ones we used. I'll try and remember in a minute. Anyway.
Yeah. And we have a second question from Rax, which is, how do you generate the cross-link structures? Have you written an in-house code to do it?
Can I just turn my speaker up just to so I can hear you a little bit better? Can you try again?
Can you hear me now?
Oh, brilliant. Yeah, sorry about
Questions are in the chat as well if you want to read them, if that helps. So how do you generate the cross-linking structures? Write an in-house code?
An excellent question. So we've done most of the work here on uncross-linked material. So this has been mainly due to this first stage in terms of mixing. So we want to look in detail at the most efficient way we can mix these together. In terms of generating the cross-linking, what the guys at Hartree have done is we have the cross-linking points on that, and they have generated the the total matrix with their own code, if you like. I'm not sure whether it's got a name or not. We'd have to ask them in order to create. We can cross-link completely. So each polymer molecule has at least 2 hydroxyls at the end, but some of them have half of them have a hydroxyl somewhere along the chain. So that question is one that we'll be addressing very, very soon. So we can either cross-link completely through their own code, or, as is often done, we don't do it completely. And it's interesting to see how the two differ. Now, one of the things we want to do, and we haven't done yet, is actually look at the molecular weight distributions here. So we haven't gone to any great lengths sort of refining the cross-linking until we then refine the molecular weight distributions and what happens there, if you like. So it's that bit's work in progress. But as I say, it's they've written their own code to do that.
We have another question from Peter. Maybe you hinted at it, but it might be possible to eliminate the plasticiser completely by design of the polymer system. Might the use of Hansen solubility parameters help to simplify formulation compatibility problems?
Right, absolutely. And you look at some of their examples, and we've done exactly that. So in other words, if you look at the adhesive industry, you can look at, you get a polymer, a rubber, and you put in a tackifier in there in many cases. However, if you look at the polymer microstructure, the architecture controls the rheology of that. So if you can do that, which we have done in the past in other systems, then you can actually do exactly what Peter said. I think it was Peter said.
Yeah, it was Peter.
And do that. Now, that, if you like, is a good goal to aim at. It's not easy at the moment to actually do that, because then we have to make another polymer system, and that's a completely different process. As you can imagine, this industry is a very conservative one, and rightly so, I think. And what we've got is we've got a tried and tested method of improving adhesion, mechanical properties, tensiles, etc., which we are aiming at first. So the quick answer is, I'm sure if we spent enough time, we could do that suggestion. Whether we have time enough in the near future to do that, I don't know. Good question.
Great. I have one very quick question for myself. The tensile tests that you showed, were they for cross-linked systems or were they uncross-linked systems?
Oh, cross-linked.
They were cross-linked, yes. Yeah. Okay.
Yeah, cross-linked. And the other bit which I haven't put in there, I talked about safety, longevity, etc., as some of the things we want to do. The beauty of these resins is that they actually improve barrier properties as well. So water and oxygen. So the materials with these resins in last much longer than anything else. They degrade much slower. They suffer from much less oxidation as well. So that's one of the other advantages on that.
Great. Thank you very much. Peter also says thanks in the chat. And with that perfect timing again, we'll move on to